Hi, my name is Ellen Vittersik, and I'll be presenting the paper, How Much Data is Sufficient to Learn High-Performing Algorithms? Generalization Guarantees for Data-Driven Algorithm Design. And this is joint work with Nina Balkin, Dan de Blasio, Travis Dick, Carl Kingsford, and Thomas Santome. So algorithms often come with a ton of tunable parameters. And these parameters can have a significant impact on the algorithm's runtime, its solution quality, and so on. Oftentimes, domain experts are left to tune these parameters by hand, which is just a notoriously time-consuming, tedious, and error-prone process. So for many of those algorithms that are typically used in practice, there's no configuration of these parameters which admits a meaningful worst-case bound. So these parameters are made available for the user to tune for their specific application. So this is true, for example, in integer programming, where a deft configuration of some integer programming solver parameters can allow you to solve very computationally challenging problems quickly. Alternatively, as was often the case in theoretical computer science, these parameters are tuned implicitly within the proof of some worst-case guarantee. But these worst-case instances can be rare or non-existent in practice. So in data-driven algorithm design, the goal is to automate the process of algorithm configuration or parameter tuning with the help of machine learning. So the input to this automated configuration procedure is a training set of typical problem instances from the specific application domain at hand. And a bit more formally, this training set is assumed to be sampled from some unknown application-specific distribution over problem instances. The output to the configuration procedure is a configuration of the parameters, which has strong average empirical performance over the training set. And by good performance, I mean, for example, good runtime, good solution quality, and so on. So whatever parameter setting we come up with using this automated approach, it should ideally also have good performance on future problem instances from the same application domain, but which aren't already in our training set. In this paper, our main contribution is a broadly applicable theory for deriving generalization bounds for data-driven algorithm design. And these generalization bounds tell you, for any choice of their parameter setting, what's the difference between the algorithm's average empirical performance over the training set and its expected performance on this unknown application-specific distribution. And these guarantees apply no matter how you tune these parameters, using an automated or a manual approach. No matter what parameter settings you come up with, you can be guaranteed on what's the difference between the algorithm's average performance over the training set using that parameter setting and its expected performance on the unknown distribution. Prior research on data-driven algorithm design has proved these types of generalization guarantees using case-by-case analyses, looking at problems from clustering algorithm configuration, integer programming, selling mechanism configuration, and greedy algorithm configuration. In this paper, we uncover unifying structure uniting these seemingly disparate configuration problems, which we use to provide very general generalization bounds. But despite the generality of these guarantees, we're still able to recover the bounds from prior research. We also provide novel generalization bounds for problems that hadn't previously been studied, including problems from computational biology algorithm configuration and voting mechanism configuration. So what does this unifying structure look like? Well, our guarantees apply to any parameterized algorithm where at a high level, the algorithm's performance, so its runtime or its solution quality or so on, is a piecewise structured function of its tunable parameters. So to have a picture in mind, you could imagine that we're varying two of these parameters, row 1 and row 2, along the x and the y-axis. And we're plotting the algorithm's performance on some fixed input as a function of these parameters. And in this picture, it's a piecewise constant function, but it could also be a piecewise linear function or piecewise something else, piecewise structured function, as I'll be more formal about later on in this talk. So what is the primary challenge in proving these types of generalization bounds for data-driven algorithm design? Well, it's really that in these combinatorial domains, an algorithm's performance is just a notoriously volatile function of these parameters. So you can imagine that we're varying one of these parameters row along the horizontal axis, and we're plotting the algorithm's performance, so its runtime or its solution quality, as a function of this parameter on some fixed input. And it's a very volatile function with many jump discontinuities. And intuitively, this is because in these combinatorial domains, if you just tweak the algorithm's parameters by a little bit, you can cause a cascade of changes in the algorithm's behavior, which causes these jumps in the algorithm's performance. So overall, there's just a very complex connection between the algorithm's parameters and its performance on any given input. Meanwhile, for those functions that we really understand well from a theoretical perspective in machine learning, there's typically a fairly straightforward connection between the function's parameters and its value on any given input. And since we don't really have this predictable structure in algorithm configuration, we have to understand what structure is there which will allow us to provide these types of provable guarantees. And in this paper, we use this piecewise structure. Okay, so now with this high-level motivation in mind, I'm going to give a specific example of a configuration problem to have in mind throughout this talk as a running example. And in particular, this will be for a sequence alignment algorithm configuration. So the input to a sequence alignment algorithm is a pair of sequences, like this pair here, and the output is an alignment of these sequences. And there are a lot of different features of alignment that we might care about, like the number of matches, the number of mismatches, the number of insertions and deletions, or indels for short, where I've matched one of these characters up with a gap character, and the number of affine gaps, which are these consecutive sequences of gap characters. So a standard algorithm for sequence alignment is defined by these three tunable parameters, row 1, row 2, and row 3. And it uses dynamic programming to find an alignment which maximizes this parameterized objective function, which is the number of matches minus row 1 times the number of mismatches, minus row 2 times the number of indels, minus row 3 times the number of gaps. Sometimes in sequence alignment, we can access some ground truth reference alignment of these sequences. This is true, for example, sometimes in computational biology. However, this requires extensive manual alignments by some domain expert. So we'd rather just run that parameterized algorithm from the previous slide. But this raises the question, how do we tune that algorithm's parameters so that ideally the algorithm's output we can guarantee is still close to some ground truth reference alignment, which is unknown. As Gusfield et al. Wrote, there's considerable disagreement among molecular biologists about the correct choice of a parameter setting. And just to illustrate the power of a well-tuned algorithm, here is a ground truth alignment of some protein sequences. And here's an alignment by an algorithm with poorly tuned parameters. So these blue regions indicate where the algorithm's output matches up with the ground truth alignment. Meanwhile, here's the alignment returned by an algorithm with well-tuned parameters. So you can see that it's able to recover much more of the ground truth alignment than the algorithm with the poorly tuned parameters. Okay, so now with this example to have in mind, I'll tell you a bit more formally about our model and the problem formulation. And we'll be adopting this learning theoretic model of algorithm configuration proposed by Gupta and Roughgarden. So RD will be the set of all parameter settings, and X will be the set of all inputs. So for example, this could be a set of sequence pairs. So one element of the set X would be a pair of sequences. A little more formally, what do I mean by algorithmic performance? Well, I'll use the notation U row of X to denote the utility of the algorithm parameterized by rho on the input X. And again, this can be a notion of runtime, solution quality, distance to some ground truth solution, and so on. So I'll use the words utility and algorithmic performance somewhat interchangeably. And just for notational simplicity in this talk, I'm going to assume that U row of X is bounded in the interval -1, 1, but this can easily be generalized to any bounded interval. We're going to make the standard assumption, which has been made for over a decade in this literature on algorithm configuration, which is that there's some unknown application-specific distribution D over algorithm inputs. This distribution is meant to model the particular application domain at hand. So for example, it could be a distribution over pairs of DNA strands that a biolab has to align on a day-to-day basis. Or it could be a distribution over pairs of protein sequences. Okay, so now with all of this notation, I can describe this notion of a generalization guarantee more formally. So let's remember that key question we want to answer, which is for any choice of this parameter setting rho, what's the difference between the algorithm's average empirical utility over the training set of typical problem instances from our application domain and its expected utility on this unknown application-specific distribution? So more formally, given a training set of sample problem instances, x1 up through xn from our application-specific distribution D, for any choice of this parameter setting rho, what's the difference between the algorithm's average empirical utility over the training set and its expected utility on this unknown distribution? If this difference is small, then we can be guaranteed that no matter what parameter setting we come up with, no matter how we optimize over our parameter settings, if we find a parameter setting which has strong average empirical utility over the training set, it will also have strong expected utility on our unknown distribution. And expected utility is really a proxy for future utility on future problem instances from the same application domain, but which aren't already in our training set. Okay, so I told you that our guarantees apply when the algorithm's performance is a piecewise structured function. So let me give you an example of one such function. And this will be in the context of sequence alignment. So to illustrate this piecewise structure, we're going to rely on this lemma that was proved over 2 decades ago in a very different context by Gusfield et al. And it tells us that for any pair of sequences, like this pair here, there's a small partition of this dynamic programming algorithm's parameter space. And there are 3 tunable parameters. In this picture, I'm just illustrating 2, but there are 3. So there's a small partition of the parameter space such that in any region of the partition, like this blue region here, the algorithm's output is fixed across all parameters in that region. So this is saying that no matter what parameter setting I use in this blue region, the algorithm is always going to output this particular alignment. And if we switch to another region of this partition, like this other blue region, the algorithm will always output this other alignment. And an immediate corollary of this lemma is that the algorithm's utility, so the distance between the algorithm's output and some ground truth alignment of these sequences, is a piecewise constant function of these tunable parameters, using the exact same partition as from the previous slide. Okay, so now with this example of a piecewise structured function in mind, let me tell you about this piecewise structure a bit more formally. So to do so, let's remember this notation I introduced at the beginning of the talk, U row of X, the utility of the algorithm, parameters by row on the input X. So if I collect a set of all such functions U row, I'll refer to it as the primal function class, and I'll denote it U. And in learning theory, we typically prove these types of generalization bounds by understanding the intrinsic complexity of this primal function class U. And we use notions like VC dimension, pseudo dimension, Rademacher complexity, and so on to understand this intrinsic complexity. But the challenge is that in these algorithm configuration scenarios, this class U is pretty gnarly. So for example, in sequence alignment, every domain element of these functions is a pair of sequences. So it's unclear how to plot or even visualize these functions U row. There's certainly no obvious notions. There's certainly no obvious notions of Lipschitz continuity or smoothness that we could rely on to understand this intrinsic complexity of the primal function class. So this is where the notion of a dual function comes in handy. So rather than fix the parameter row and vary the input X, we could just as well fix the input X and vary the parameter setting row. And we get the algorithm's utility as a function of these tunable parameters. And as you would hope, Ux of row equals U row of X. And if I collect the set of all such functions Ux, I'll denote it U star, and I'll refer to it as the dual function class. And these dual functions are pretty nice because they have this simple Euclidean domain, RD, and they often have ample structure, which we can use to bound the intrinsic complexity of the class that we actually care about, U, the primal function class. So what I've been alluding to throughout this talk is that across all of these different domains, clustering, integer programming, selling mechanism, greedy algorithm, computational biology, and voting mechanism configuration, these dual functions, the algorithm's performance or utility as a function of its parameters is piecewise structured. It's piecewise constant, piecewise linear, or piecewise something else. Great, so now with this notion of a piecewise structured dual function, I'll tell you about our main theorem. And to do so, I'll tell you a bit more about this notion of intrinsic complexity from learning theory. So the intrinsic complexity, I'll denote as CG, a real value of a function class G. And in learning theory, these notions of intrinsic complexity intuitively are meant to capture how well do functions in this class G fit complex patterns. So for example, these sign functions would be more complex than the set of constant functions because these sign functions are able to fit more complex patterns. There are a lot of specific ways to quantify intrinsic complexity. In this paper, we use VC and pseudo dimension. So now with this notion of intrinsic complexity, I'll give you the flavor of our main result, starting with a picture. So let's say that we've got these two parameters, row 1 and row 2. In general, there can be any number of parameters, but in this picture, let's say there are 2. And we're plotting the algorithm's utility as a function of the parameters, the dual function, on some fixed input X. And again, this is a notion of the algorithm's runtime, its solution quality, its memory usage, and so on. So let's say that for any input X, there are these functions G from some set G, which partition the parameter space. So in this picture, there are 3 such functions G partitioning the parameter space into 6 regions, such that in any region, their algorithm's utility, the dual function, equals some function F from some set F. So in this picture, F is the set of all constant functions, but it could be any set of functions. So let's say that this structure holds for any input x. We proved that with high probability for any choice of this parameter setting, the difference between the algorithm's average empirical utility over the training set and its expected utility on our unknown distribution is bounded by the square root of CF plus CG, where CF and CG are the intrinsic complexities of the set F of piece functions and the set G of boundary functions. I'll be more specific about this on the next slide. Times log k, where k is the number of boundary functions, divided by n, where n is the size of our training set. And specifically for those of you familiar with learning theory, we proved that the pseudodimension of U, the primal function class, is bounded by the pseudodimension of the dual of the set of piece functions plus the VC dimension of the dual of the set of boundary functions times log k, where k is the number of boundary functions. So to give you an idea of why the duals are showing up in so many places in this theorem, I'm going to describe a key lemma that we prove in order to prove our main result. So you can think of each of these boundary functions G as a binary function, which splits the parameter space into two regions. One where the parameters are labeled -1 and the other where the parameters are labeled +1. But we don't just have one boundary function, we have k boundary functions. And to understand better the partition of the parameter space that these boundary functions induce, we want to know, given k boundary functions, how many sign patterns do they make? So in this picture, we've got 3 boundary functions, and they make a total of 7 sign patterns of which side of the boundary function is the parameters on. So written just mathematically here, we want to know for these k boundary functions, as we vary the parameter setting, how many sign patterns do they make? Well, to answer this question, we rely on this classic lemma from learning theory, Starr's lemma, which tells us that for any k parameter settings, row 1 up through row k, if we fix those k parameter settings and vary the function g, how many sign patterns do we get? Well, this is bounded by e times k, the number of parameter settings, to the VC dimension of g, g being the set of boundary functions. But this doesn't quite answer our question, because here we're fixing these k parameter settings and varying the function g, whereas to understand the partition of the parameter space, we want to fix the k boundary functions and vary the parameter setting row. So this is where transitioning to the dual function comes in handy. Because if you transition to the dual function, then we can bound the number of sign patterns these k boundary functions make by e times k, the number of boundary functions, to the VC dimension of the dual of the set of boundary functions. So hopefully this gives you an idea of why transitioning to the dual functions can help us understand this partition of the parameter space into these piecewise simple regions. And ultimately, this kind of understanding allows us to prove our main theorem. Okay, so now I'll give an application of our guarantees back to our running example, sequence alignment. So let's remember that lemma I proved, or I described earlier in this talk, which says that the algorithm's utility is a piecewise constant function of those parameters. So the dual function is piecewise constant. Just plugging in what we know about this function to our main theorem, we get that with high probability for any choice of our parameter setting, the difference between the algorithm's average utility over the training set, so utility here being the distance to some ground truth alignment, and its expected utility, our unknown distribution, is bounded by the square root of log the maximum length of these sequences divided by n, where n is the size of our training set. So now I'll just wrap up with some conclusions. So overall, we saw this unifying structure, this piecewise structure, dual functions, which connect these seemingly disparate configuration problems: clustering, integer programming, ceiling mechanism, greedy algorithm, computational biology algorithm, and voting mechanism configuration. And we use these structure to provide these extremely generalization guarantees. So with that, I'll wrap up. Thank you.